Welcome back to The Explainer. Today, we're going to fundamentally shift how you think about neural networks. If you've ever felt kind of bogged down by the dry, tedious arithmetic of machine learning, I want you to completely clear your mind of that right now. We are stepping out of the spreadsheets and into a dynamic, geometric reshaping of space. Trust me on this one, once you see AI through this geometric lens, you're literally never going to look at a transformer model the exact same way again.
So, we all know how to mechanically multiply two matrices together, right? Row meets column, multiply, add, rinse, and repeat. But we've been leaving this massive question hanging in the air. What does that operation physically do to space? Because it's one thing to crunch the numbers. It's a completely different thing to actually understand the physical reality of what those numbers represent.
Okay, let's just dive straight into our 6-part roadmap for today. We'll be looking at 1. Reshaping space itself. 2. A simple geometric example. 3. Transforming AI embedding space. 4. Rotation in attention heads. 5. Breaking the linear wall. And finally, 6. The geometry of intelligence.
Starting off with Section 1, Reshaping Space Itself, the Paradigm Shift.
All right, here is the reframe that absolutely changes everything. A matrix isn't just a calculator for numbers. A matrix is actually a compressed instruction for reshaping space itself. Think about it. Every matrix you've ever multiplied was secretly telling a set of points how to stretch, rotate, flip, or collapse. Picture two arrows in your mind, one pointing right and one pointing up. A linear transformation simply asks, after applying this matrix, where do those two arrows end up pointing? Once you know that, you automatically know what happens to absolutely every other point in space. Why? Because linear transformations preserve straight lines and evenly spaced grids everywhere at once. So a matrix isn't some static lookup table. It's a universal rule for reshaping the entire universe of your data simultaneously.
Let's ground this with Section 2, a geometric example, the row swap matrix.
Take a matrix that simply swaps rows, so zeros on the main diagonal, ones on the other. If you apply it to a point, let's say a coordinate sitting right at 3, 5, it immediately turns it into 5, 3. It just trades the x and y values. Simple enough if you're looking at a spreadsheet, but what does that actually look like geometrically?
Well, this brilliantly illustrates the sheer power of what we're talking about. Geometrically, this isn't just a machine calculating points one by one. This single matrix performs a simultaneous mirror flip of the entire 2D plane right across a diagonal line. Every single point in space all at once gets reflected. And that's not because the matrix ran a loop and calculated each point individually, but because it defined one uniform rule that applies everywhere forever. This idea, a linear transformation, is the single geometric fact sitting underneath every layer of every neural network ever built.
Moving on to Section 3, AI embedding space. High-dimensional points.
Now, here is where we bridge the gap between human language and math. Every word, every image patch, every audio frame that goes into an AI model gets converted into a point in space, an embedding. Suddenly, raw inputs like king, queen, cat, and dog aren't just text anymore. They become actual geometrical coordinates sitting in a high-dimensional embedding space.
And here's the crazy part. This space has real baked-in structure. Traveling through this meaning space reveals that the direction you move to get from man to woman is remarkably similar to the direction you move from king to queen. That's no coincidence. It's a linear relationship baked directly into the geometry by the training process, which is honestly just incredible when you really think about it. So as data flows through a transformer, every single layer applies a linear transformation to reshape, rotate, and reorganize this massive point cloud, literally moving words into geometric arrangements that make the model's ultimate task easier to perform.
Let's look at how this works in practice with Section 4, Attention Rotation, Multiple Viewpoints.
You've likely heard of attention mechanisms projecting embeddings into queries, keys, and values. Well, guess what? Each of those projections is just a linear transformation. Think of them as different geometric lenses. Each one is rotating and reshaping the exact same underlying meaning space into a brand new perspective. And this perfectly explains why transformers use multiple attention heads. Each head applies its own unique linear transformation, its own specific rotation to look at the data differently. So one head might rotate the space to clearly see grammar, while another head is simultaneously rotating the space to reveal emotional sentiment.
And it gets even more literal than that. Modern language models use something called rotary position embedding. This is a pure linear transformation that encodes word order using literal rotation matrices. It rotates a token's vector by a specific angle based purely on its position in the sentence. It does double duty flawlessly. It perfectly preserves the geometric meaning of the word itself while quietly encoding exactly where it sits in the sequence, completely through rotation.
Section 5. Breaking the linear wall. The need for curves. So the crucial point we have to understand is this. However many linear transformations you chain together, say you rotate, then stretch, then flip, then rotate again, the combined mathematical result is still just one single linear transformation. You can never escape straight lines in flat space using linear transformations alone. Without help, a 1,000-layer neural network mathematically collapses down to the exact same power as a single-layer network. And this is precisely why neural networks inject nonlinear activation functions between layers. They add these small nonlinear bends or twists to the space. Alternating flat transformations with these small bends is what allows the model to carve out genuinely complex curved decision boundaries.
This geometric understanding completely unlocks why techniques like LoRa fine-tuning work so beautifully. If you want to teach an AI new tricks, you could do full retraining, which means rebuilding these massive spatial transformations from scratch. And yeah, that is incredibly expensive. Or you use LoRa, which simply learns a small additional linear transformation and adds it right on top of the original one. Geometrically, it's just a small spatial nudge. For developers, this is a massive sigh of relief. It saves unbelievable amounts of compute, time, and money because you were just slightly tweaking the geometry, rather than tearing down the entire universe and rebuilding it.
Wrapping things up with Section 6, Geometry Intelligence, Reshaping Space.
So what should you really take away from this explainer today? It's that every single AI model, from a tiny classifier all the way up to a trillion-parameter large language model, is just reshaping meaning space until a task becomes solvable. They dynamically bring together these exact geometric concepts. Neural networks, they're just chains of flat transformations and tiny bends. Attention heads, rotated viewpoints. Position encoding, literal rotation. And the entire multi-million-dollar training process, it is honestly just a massive search algorithm hunting for the exact perfect sequence of reshaping instructions to turn a chaotic cloud of raw data into structured intelligence.
But that leaves us with a pretty fascinating, provocative question to ponder. When you twist, stretch, and reshape an entire universe of data, what exactly happens to the special directions in space that a transformation leaves completely unchanged? Because those unmoving lines are called eigenvectors, and their lengths are eigenvalues. And understanding them is the absolute key to unlocking what a trained model has actually learned. But we'll have to save that geometric rabbit hole for our next explainer. Thanks for joining me.